In this lesson, we will go over the what's called Fundamental Theorem of Calculus, and hopefully by the end of the lesson, you'll be able to understand the relation between indefinite and definite integrals and use the Fundamental Theorem of Calculus to evaluate definite integrals and maybe perform a couple other tasks. However, we start the lesson by reviewing what we have been introduced to so far, and that is we're looking at indefinite and definite integrals, and we now wonder what these two concepts have actually in common. On the surface, these two ideas seem completely unrelated. One is about finding antiderivatives, and the other one is about measuring the area. One is somewhat not geometric in nature, and some may say it's algebraic in nature, and the other one is absolutely geometric in nature. So the question is that we're having now is why do they even use the same notation, and why are they both called integrals? Because it seems like they're just two completely different things. And the Fundamental Theorem of Calculus will answer this exact question. It establishes the connection between the two different types of integrals, and moreover between two different branches of calculus, differential calculus and integral calculus. And before we state the theorem, I would like you to acknowledge how non-trivial is the task that we are presented with. And let's see. My pen turned off. There you go. So what we're trying to show is that definite integral is, so we already know that indefinite integral is the opposite of differentiation. So what we're trying to show is that definite integral is sharing somehow its nature with indefinite integral. And one way to show it is that definite integral is also the opposite of differentiation somehow. So it's very tempting to just say, well, isn't it true that if you take a definite integral and differentiate it with respect to, and here's another question, with respect to what? You're going to differentiate it because x is a dummy variable, it's not really a variable, so you can differentiate it with respect to any variable you want. But the bigger issue is that we have a number on the left, and we're differentiating a constant, and the answer is always going to be 0. So there's nothing really meaningful about saying something like this. Now, it could also be tempting to just say like, well, forget about definite integral. Isn't it at least true for indefinite integrals that you just differentiate this and you end up with what exactly? Well, very tempting to say you're going to end up with f of x. However, is that true? Well, on the left side, we have not a single function, but rather the what's called the general antiderivative, which is a family, infinitely large family of functions. And we don't really know how to differentiate more than one function at a time. We're kind of lucky that all those antiderivatives have something, in common, but in general, differentiating family of functions is not something that we have learned in Calculus 1 class. So this claim is also kind of not so meaningful or questionable, so to say. And it's also not immediately obvious what does the area under the graph, or the net area between the graph and the x-axis, have to do with antiderivatives, right? Or derivatives, or anything for that matter. So what is the deal with this whole two different things being called integration? Well, we're about to find out. First, we're going to introduce a new term. I'm going to copy and paste it here. And we call, for some continuous function f of x, we create the following. Let's go through it one line at a time. For some continuous function f of x over some interval from a to b, we create a new function, call it capital F of x, similar to the notation that we adopted for antiderivative. Is it a coincidence? Well, we'll find out. But we introduce this new function, capital F of x, in this what appears to be a strange way. First of all, there's nothing strange about using integral with a variable in one of the limits to introduce a function. For example, there are well-known functions called Fresnel functions, named after a French physicist, Augustin Fresnel, and those functions have many applications in physics and even in engineering. So it's a pretty standard way of defining a function. So we just need to understand how is it a function of x when x is in the limit of integration. But let's finish reading the definition. So we call this the cumulative area function of f of x on a to b. So cumulative area means we do want to draw a picture, and here's your function f of x. Here's the interval from a to b, and I guess, sure, the function is f of x, but here we're not using x, we're using variable t. So let's change this to t and make this f of t. But t is a dummy variable. The true variable here is x. And x is somewhere on the interval from a to b. And now let's take a look. So x varies, and what varies with x? It's the area, the net area between the f of x on the interval from a, not f of x, but rather f of t, on the interval from a to x. So x changes, and this area also changes, and this area right here is what we're referring to as f of x. This area absolutely depends on this x, and therefore it makes sense to make it a function of x. So x goes to the right, the area increases or decreases, depends on the function, but changes. So hopefully it is clear now that this defines a function of x in this, again, initially we could think of it as a strange way, but there's nothing really strange about this. It's a pretty cool way of introducing a function. And the name also makes sense. It's a cumulative area function. So it tells us how much area is between the graph and the x-axis as you go from a to x. So x goes to the right, the area changes. X goes to the left, the area changes. But as x goes from a to b, it tracks the accumulation of area as x goes from a to b. And now that we understand that f of x is a function, we also know that it's a continuous function because area doesn't change suddenly. And moreover, it's also a differentiable function, meaning the area changes in a nice, smooth way. And the question now is, well, if it's differentiable, what is the derivative of this function? So now that we have, let me bring this over here. Let me clean up I cleaned up too much. Let me clean up all the drawings and ask the question again. So now that we understand that f of x is a function, we want to know what is the derivative of this function. In other words, if x increases a little bit, by how much does the f of x increase? And intuition is very simple. If you accumulate the area and you change x, let's say by some very small quantity, delta x, then the function changes output by what? Since it's the area, what's the additional area if x changes by delta x? Well, it's this rectangle. But the area of this rectangle is f of x times dx. And that, well, not dx, but like rather delta x. And that's kind of the hint. So how much does this area change per change of input? Then delta x goes away, and the answer is f of x. So that's kind of the intuition behind it. But the point is, an attempt to answer this question leads us to the following statement. Derivative of a function defined this way with respect to x is simply equal to f of x. And this is not the exact proof, but this is just the idea behind the proof. All right, so let's unpack this statement. This statement is what we're going to refer to as the Fundamental Theorem of Calculus, part 1. Let me bring it over one more time. So we abbreviate the Fundamental Theorem of Calculus, FTC, and we call this particular statement FTC1. This is what it says. And what it actually says is that what we have here inside is the cumulative area function. And it says that cumulative area function is not there are many antiderivatives, but an antiderivative of f of x, which is pretty interesting statement. So one way we can test our understanding of this theorem is to try to differentiate something like this with respect to x. And by Fundamental Theorem of Calculus 1, this derivative will be simply the integrand evaluated at x. That's it. You can try yourself and differentiate the Fresnel function, which is defined like this. With respect to x. I'll give you some time to think about it, but I'll start doing it, and so you can pause the video and work on it, but I'll start solving it in 3, 2, and 1. So derivative according to Fundamental Theorem of Calculus, part 1, is simply sine of pi x squared over 2. And that's it. That's the answer. That's that's how simple the application of the fundamental theorem of calculus is. However, we can generalize the fundamental theorem of calculus. Not generalize, but because what it does, it just tells us how to differentiate a certain function. We can now apply the fundamental theorem of calculus in combination with other differentiation rules. So in general, we can apply it with the chain rule and differentiate a function defined like this, where we have functions of x in the both upper and lower limits of integration. Conceptually speaking, this is like, it's not the area function anymore. It's like some not necessarily algebraic construction, but it is pretty abstract. So we're not really concerned in terms of what does this mean, but purely symbolically, we don't have an issue with integrating something like this. So we have integral. If we ever presented with a problem like this, I'm going to throw epsilon over there just to show you that it doesn't matter what letter we use here. And integrate this from square root of x to x cubed. How do we differentiate this function? Well, according to this rule, we apply the chain rule carefully. So it's a chain rule combined with the subdivision rule. But the point is, according to this rule, we evaluate the integrand at the upper limit first, then multiply by the derivative of the upper limit, and subtract the evaluation of this integrand at the lower limit times the derivative of the lower limit. And that's it. Now, I would like you, so this was me doing an example, now I would like you to try and find the derivative of this function. Integral from ln x e to the x square root of t cubed plus 1 dt. I'll start solving it in 3, 2, 1. According to this rule, the answer will be evaluation of the integrand at the upper limit first times the derivative of the upper limit minus the evaluation of this integrand at the lower limit times the derivative of the lower limit. And that's it. That's how we use the fundamental theorem of calculus, part 1. Now we're going to state the second part of the fundamental theorem of calculus, and I'm just going to copy and paste it here. Part 2 of the fundamental theorem of calculus looks like this. So what it tells us is that the net area between the graph of the function and the x-axis on the interval from a to b can be found by evaluating the antiderivative, any antiderivative at the right endpoint of the interval, and subtracting the value of that same antiderivative at the left endpoint of that interval, which is pretty weird if you think about it. How is this exactly related? But here's one explanation. Since the cumulative area function is actually one of the derivatives, we can see why this statement actually makes sense, because if you express cumulative area function at b like if we go back here, right here. So we claim that cumulative area function is an antiderivative of f of x. Here we're saying to find the definite integral, it's sufficient for us to pick any antiderivative and evaluate it at b. So why don't we pick the cumulative area function as that antiderivative, and there's nothing wrong with that. And when you do that, you will see that when you pick a cumulative area function and you evaluate it at a, we're going to get integral from a to a of f of t dt, which is 0. And when you evaluate this at b, we're going to end up exactly with the integral from a to b f of t dt. So when you take this back over here, you see how with using cumulative area function as an antiderivative, we end up with exactly this. Well, not f of x, but f of t, but we know that this is a dummy variable, so it's just a placeholder, so it doesn't matter if you use x or t, so these are the same integrals. So that's kind of the idea behind why this theorem is true, but in terms of what does this theorem tells us, it's actually, that's what's more important. It allows us to actually find the area under the graph by simply finding the antiderivative first and then doing this subtraction, which kind of becomes more of a process than just an application of the formula. And let's see how this process actually works out by doing an example. So if we're looking for the integral, definite integral of something simple, let's say standard parabola, in the past, what was our option? What was our options? What were our options? We didn't have many. We could have done it visually, and we could have done it using the limit of a Riemann sum. That was it. Either way would be, visually probably would be like a dead end. Using the Riemann sum would require some careful execution. Now, however, we can use the Fundamental Theorem of Calculus Part 2 and simply conclude that the integral, the definite integral of x squared is equal to the indefinite integral of x squared evaluated at b minus the indefinite integral of x squared, same one, evaluated at a. So the question is, the only question we have is like, what is an indefinite integral of x squared? And previously we developed the rules for finding indefinite integrals, and we know that indefinite integral of x squared is simply 1/3 of x cubed. So to apply the Fundamental Theorem of Calculus, we have to evaluate 1/3 of x cubed at 4 and subtract 1/3 of x cubed evaluated at 1. And that will give us the answer. So 1/3 times 64 minus 1/3 is equal to 63/3, which is 21. This was easy, so this is just arithmetic. So the hardest part was right here, actually doing the Fundamental Theorem of Calculus. Now, to help us to be more efficient at using the Fundamental Theorem of Calculus, we're actually going to adopt the following notation. In between, I need to clean up this. In between the left side and the right side of this statement, we're actually going to enter this. We introduce the following notation. And when you draw the vertical line and you put A and B, like this means exactly that. So let's do the same problem one more time, and let's see how much smoother the process is now. we're going to find the antiderivative first. We're going to use this notation. And we understand this notation now, and we plug the upper bound first minus the lower bound. And that, of course, is the same. Now I want you to try and use the Fundamental Theorem of Calculus by doing the following problem. I'll start doing it in, well, so feel free to pause and work this out yourself, but I'll start solving this in 3, 2, 1. So using the same notation, I'm going to find the antiderivative of e to the x, which is e to the x. I'm going to use this notation. I'm going to express it like this, and I'm going to now interpret this notation as the difference of e to the power ln of 3 and e to the power negative ln of 3, which is just 3 minus 1/3, 8/3. Now, we summarize this result as an additional way of evaluating the, or rather a definite integral. And here are the steps. Experiencing technical difficulties here. Here's the process. I'll copy it and paste it, and the rest is just practice. So to compute a definite integral, we can now find an antiderivative, use FTC2, and then evaluate that expression using our arithmetic skills. And let's do a couple problems. I'm going to pause this recording and find a couple additional problems in the book. All right, I found a list of problems in the book. So this is what they look like. And let's pick a couple problems and solve it together. Let's do maybe 28. So in 28 we have integral from 0 to 4 of 4 minus t times square root of t dt. The tricky part is actually finding the any antiderivative. And what we're going to do is we're going to distribute square root of t and write it in exponential form. And when you do that, we can now use our integration skills and the power rule to find antiderivative of this. So it's going to be 4 times t to the power 3/2 divided by 3/2 minus t to the power 5/2 divided by 5/2. This is antiderivative, and we're going to evaluate it between 0 to 4. Before we evaluate it, let's simplify it. So we have 8t to the power 3/2 over 3 minus 2t to the power 5/2 over 5. Evaluate it from 0 to 4 and plug in 4. So when you're doing this, I recommend drawing 2 sets of parentheses and slowly plug the upper limit first and then the lower limit next, so you don't lose anything. This whole thing ends up being 0, so we just need to focus on evaluating this. Square root of 4 is 2, 2 cubed is 8, 8 times 8 is 64, so we have 64 over 3, minus square root of 4 is 2 to the power 5, 32. 32 times 2 is 64, minus 5. So we have 128 over 15, something like this. That's the final answer. Now, you can check your work with Desmos or any other technology, but the point is you got to learn how to perform these steps yourself. And again, half of the success is in being able to organize your work and demonstrate your skills in a clear way. Try another problem yourself, and if you have questions, reach out to me when you see me next time. Now, it's worth making a note that since finding a definite integral essentially depends on one's ability to find the corresponding indefinite integral first, the skill of finding an antiderivative becomes central when it comes to definite or indefinite integrals. Either way, you gotta know how to find the antiderivative. So practice that skill. You cannot be too good at it anyway, so keep on practicing. Now, let's end this lesson by observing something remarkable. So far, we've used the fundamental theorem of calculus to turn a definite integral into indefinite integral. So we claim that integral from a to b of f of x dx is related to the antiderivatives. So that's beautiful. So we can use indefinite integral to express definite integral. However, it is not a one-way street. It is also possible to use definite integrals to express indefinite integral somehow. How exactly? Well, let me show you. We're going to take a look at, start off by looking at the fundamental theorem of calculus, part 2. And we're going to slowly transform it one piece at a time. So we know this is true. We now know that this doesn't have to be x. It could be t. So let's write t over here. We now know that this doesn't have to be a fixed value b. We can actually introduce x in the limit of integration and put x over here. And now we can algebraically move f of a to the right-hand side, or rather left-hand side, and then swap the sides to end up with this by itself on one side. And on the other side, we're going to have the integral from a to x, f of t dt, plus f of a. In this expression, this is a definite integral. So it wasn't definite integral from a to b, but it was a definite integral from a to x. And because x is an outside variable, we definitely cannot use that variable here. So we're going to just pick another dummy variable, such as t. And because every indefinite integral has like constant of integration c, in this case, this value is going to serve as the constant of integration. So it turns out that we can use indefinite integrals to express definite integrals, and we can also use definite integrals to express indefinite integrals, and it's all because of the fundamental theorem of calculus. So what previously, remember, I just want to point out that we started off by looking at this table and wondering what is the relation between these two visibly different things, and now not only we found the similarities, but we found the way how to express one using the other one. And alternatively, like not alternatively, but this like this understanding and this ability to express an antiderivative using this notation allows us to see the following. This is what we previously called the cumulative net area function. And of course, the derivative of cumulative area function, according to the Fundamental Theorem of Calculus part 1, is equal to the f of x. So this shows us that, which is the conclusion of the Fundamental Theorem of Calculus part 1. So by understanding part 2, we were able to arrive back to part 1, which demonstrates in a very elegant way that the two parts of the Fundamental Theorem of Calculus are not separate results, but rather two sides of the same coin, which is why they're always, or not, maybe not always, but traditionally presented as a pair and two statements of what we call the Fundamental Theorem of Calculus. So this is a good place to end this lesson. Again, the main takeaway is the theorem itself and its application for finding definite integrals. So this is kind of the main skill, which requires practice. But practicing this depends or relies heavily on your ability to find the antiderivative. So practice that too. If you have any questions, let me know. But this is the end of lesson on the Fundamental Theorem of Calculus.